I'm Dr. T and welcome to my office. So today I'd like to talk about phase changes. So phase changes are going to be when a substance transitions from one state of matter into another. So solid to liquid, solid to gas, liquid to gas, whatever you'd like. And in doing so, of course, it's going to be changing how the atoms are arranged within that substance. And there's going to be a small multitude of factors that are going to determine when and how those phase changes are going to take place. Or I should say, really at what temperature, because the governing factor of what something is, whether it's a solid, liquid, or a gas, or plasma, is going to be what temperature it is. So let's zoom in and think about our substances. So substances, of course, as we know, are made up of atoms and or molecules, which of course molecules are made of atoms. So to go from one phase to another, we're not talking about a chemical reaction, we're talking about a physical change. So if you've got molecules, we're not breaking apart those molecules. We are simply taking the molecules and separating them from their neighbors. Or sticking them, packing them nice and tight in with neighbors, depending on which way you're going. Now, what's going to start affecting this? Well, of course, temperature, as I mentioned earlier. As you raise the temperature, the atoms and molecules are all vibrating, and they're vibrating more and more. This is what temperature is this vibration of atoms / molecules. Now, what's counteracting that vibration is going to be two other properties. First is fairly intrinsic to the material, and that is what type of intermolecular forces are acting on the molecules, or acting through the molecules, I probably should say. Each one has different abilities to attract other molecules. Of course, this would be things like hydrogen bonding, London dispersion forces, ionic bonds, and the like. The stronger these are, the more they're able to hold something together and keep the material as a solid or a liquid. And thus we can see materials such as water, which have hydrogen bonds, actually gets you a pair of hydrogen bonds, is a liquid at a fairly high temperature. Whereas a similarly sized molecule such as methane, which does not do hydrogen bonding, is going to be a gas at room temperature. Now, larger molecules, of course, at the same temperature, because temperature is not a description of the velocity of the vibration, but the kinetic energy of the vibration. Larger molecules typically are going to have more intermolecular forces, just because there's more molecule to work with, and because of their larger mass, the actual velocity of these guys bouncing around is going to be lower for the same kinetic energy. Because remember, kinetic energy is 1/2 mv squared. If m goes up, v must go down. Now, the other property that's actually fairly quintessential for whether or not something is going to be doing a phase change that is more extrinsic to the material is that of pressure. How hard are they being squished together? What force is being exerted on them other than them simply vibrating? This, of course, could be from, say, something sitting on top of them and physically pushing them down, or collisions with gas particles around them. Thus, we wish to look at pressure, or the force exerted over an area, as the other major contributing property to where a phase change will happen with respect to temperature. So with this said, we can make phase change tables, like this guy over there, which relates temperature and pressure. On these are going to have a couple of different zones on them. These zones would be things such as the area for the solids, the gases, and the liquids. Now, every substance is going to have different intermolecular forces, therefore it's going to get its own graph, because the lines will be in slightly different spots. In fact, mixtures, because a mixture has multiple things in there and different ways for them to interact, mixtures will cause the graph to change as well. But let's take a look at this particular graph. Of course, we've got ourselves some solids. These are typically going to be occurring at relatively high pressures and relatively low temperatures, although there are some exceptions. Substances that crystallize in such a way that the solid is a lower density than the liquid will actually melt when placed under pressure. Water is one such substance, and therefore the slope of the line is actually somewhat different than you would expect for water for that solid-liquid interface. Now, at low pressures and high temperatures, typically you expect to see a gas. Going from solid to gas is known as sublimation, And going from gas to solid is known as deposition. These two phase changes are typically not discussed as much because good old water actually does do them, but doesn't do so quite as commonly as you would expect. If you notice in your freezer, your ice cubes will slowly shrink, and your meat, if you didn't seal it up nice and tight, will start to get freezer burnt. This is due to sublimation. Water is leaving the ice cube and or the meat, going straight into a gas, and then you will also find that you get all of this really annoying frost buildup on the inside of your freezer. Obviously, if you have a no frost freezer, that tends to be a bit less because that's the whole point of the fancy freezer, but either way, you still get this. And this is water going straight from a gas to a solid and depositing itself on the stuff in your freezer. Of course, this can then ruin meat, which is not fun, so seal up nice and tight your meat. Okay, so we've got ourselves our gases. The third major phase that we normally talk about is that of the liquid. And of course, liquids are going to kind of be an intermediate, medium to high temperature and medium to high pressure. And thus you get this kind of Y-shaped graph. Where the three lines intersect is going to be the triple point. Conveniently for us, the temperature and pressure on Earth is close to the triple point of water, which is why we can see both ice, liquid water, and water vapor on Earth in situations where we're not dead. Now, going from solid to liquid, that's going to be melting. Liquid to solid, freezing. You already knew that. Liquid to gas, that's usually described as vaporization. Boiling is kind of a specific case study in vaporization. And same for evaporating. So usually we call that vaporization. Going from gas to liquid would be condensation. So once again, you're familiar with it. Now, if you look at the graph a little more carefully, you will notice that the line separating liquid from gas does not keep going. It stops at something called the critical point. The critical point describes this interesting boundary. Beyond this, you get a region which is not a true state of matter, although has some rather unique properties. This is called a supercritical fluid. This region is most noted in that it has properties of both liquids and gases, and as such can actually do some really interesting and bizarre things. Specifically, though, you can go from a liquid to a supercritical fluid without actually boiling or vaporizing your liquid. Likewise, you can go from a supercritical fluid to a gas without a phase change. Yeah, I know. Trippy, right? Yeah. So you have this really interesting region. There are unique properties to this. Water, when it's in a supercritical fluid, actually behaves like a hydrophobic or not water-liking solvent. Supercritical carbon dioxide has now become a popular way of removing caffeine from coffee beans. And other potential cleaning applications. This is a new and burgeoning field of science trying to understand the many uses of supercritical fluids. Above, of course, going even higher in temperature is going to be the plasma, although this is a range that, as chemists, we don't usually deal with. This is known as ionization once you transition into the plasma phase of matter. And yeah, that's getting really hot because it's so hot you're vibrating so much that the electrons are bouncing off of your atoms, and you now have a gas effectively that's comprised of cations and electrons, which is hot to say the least. Now, when you are looking at these phase changes, in these cases, then you have an interesting thing to look at when you're dealing with the heat of these, because this is a change. You can no longer use the calorimetry equation when you change phases or when you do any form of change. The heat described in a phase change or any change like a chemical reaction is known as enthalpy and is given the abbreviation delta H for its variable. Any particular phase change or chemical reaction will have a delta H. A delta H that is negative is going to be exothermic, because remember, you're talking about the thing, so if it's giving off heat, then it's going to be losing heat, therefore it will be negative. A delta H that is positive will be endothermic. It is sucking up the heat. So ice melting, endothermic, ice freezing, exothermic. The equation to use this will then be, of course, Q equals delta H times the amount of substance. Depending on which form your delta H happens to be in, the amount of substance may be described in grams or it may be described in moles. please make sure to read the fine print because, of course, a gram of water and a mole of water are not the same thing. It's a factor of 18 difference. And thus, fine print is important for figuring out which number you happen to be using. We can also couple a change, once again, use of delta H, in conjunction with our calorimetry equation. So we could say delta H times the amount of substance, once again, either in moles or grams, is going to equal the mass of the surroundings, whatever it is heating up or cooling down, times the specific heat of the aforementioned surroundings, times the change in temperature of the surroundings, and then because the Q has a sign change, because heat is traveling from one into the other, there is a -1, giving us the equation delta H times M if we're going to be using mass, or N if we're going to be using moles, equals mass times specific heat times delta T times -1. So with that said, have a wonderful day, and I will see you in later videos.